this video is going to go over unit analysis, conversions, and then standard form. Three very important topics to know in physics, right? Or any sort of class of measurement in general. So, I love Mario Kart. I'm wearing the Mario Super Mario 3 shirt here. I love Mario Kart. It's a fun game. It's a game where you get to race around with different characters and throw objects at each other, and it's basically a racing game. Very popular. But anyway, so here's a fictional track. It's a circular track with Mario. That's why I drew the. This is the top view of Mario's kart. This red hat here. I'm playing as Mario, and I'm going around this track. And the distance around the track is 5,000 meters. All right. And it takes me 1 minute and 9 seconds to get around the track. That's my best lap, right? So I want to answer a couple questions here. What's Mario's average speed around the track in meters per second? What's his average velocity around the track in meters per second? And what's his average speed in miles per hour? Something we're more used to working with, miles per hour versus meters per second, right? So let's start with the first one. What's Mario's average speed in meters per second? So the equation for average speed, a lot of times speed is labeled as V. I know but speed is just distance divided by time. It's the distance traveled divided by time. So the distance traveled is 5,000 divided by time. But we want meters per second. So we want 5,000 meters divided by the time in seconds. Well, I have my time in minutes and seconds. So to figure out how many seconds are a minute and 9 seconds. Well, I know a minute is 60 seconds. Write down 60 seconds. But I'm going to add on 9 seconds because there's an additional 9 seconds. We'll put that in parentheses because it's 60 plus 9, or I can just write 69 seconds. So now I'll just take my handy dandy calculator, another very useful tool for you. I encourage you to get a real basic calculator for this class. Anyway, I'll take 5,000 divided by 69, and I get an average speed of 72.5 meters per second. Now, if you notice, the units do work out. I have meters on top, seconds on bottom, so the units of meters per second end up being the units that I end up with. 72.5 meters per second. That's pretty fast. All right, we're going to figure out what that is in miles per hour in a bit. Question 2, what's Mario's average velocity in meters per second? So velocity also has a symbol for V in physics. And when we figure out its average velocity, the velocity is displacement divided by time. Now, displacement is the distance from the starting point. We have to figure out how far did Mario travel from his starting point. So he started here, he went around the track, and he ended up here. So what's his displacement? 0. He traveled 0 meters from start to finish. Huh. Well, he still took 69 seconds to get back to 0. So I write down 69 seconds. But his average velocity ends up being 0 divided by 69, which is 0 meters per second. It's kind of interesting. So his average velocity is 0, but his instantaneous velocity is how fast is he going right at that instant. And that was actually the same as his speed. His instantaneous velocity is 72 meters per second this way, and then it was 72 meters per second this way. Then it was backwards or down 72 meters, then it was this way 72 meters. So they all canceled out and ended up giving him a 0 in the end. But at any given time, he's traveling 72, or positive 72, or 72 to the left, or 72 to the right. Slide to the left, slide to the right. Right. Let me get the example. All right, what's Mario's average speed in miles per hour? So we're going to go with the speed one, not the velocity one, because it's too easy. So what we're going to do is we're going to start with what we know. The way you convert from one measurement to the other measurement is you start with what you know. Here I know he's traveling 72.5 meters per second. So we'll write that like this. 72.5, that's my numeric value that I know. So I start with that, and I write down meters. He's traveling 72.5 meters in 1 second. So I'm actually going to write that as a ratio of how many meters does he travel per second. So it's like saying he would travel 72.5 meters in 1 second. That's what that's saying. That's what that 72.5 meters per second is exactly saying. What we're going to do is we're going to multiply by conversions to try to get to our destination. Our destination is miles per hour. We want to end up with miles on top and hours on the bottom. Now, we have meters and seconds, which means that the meters has to go away and it has to be replaced with miles. So I'm going to write miles on top. The thing I want on top is miles. And since I want to get rid of it, I want to write down meters on the bottom. so they cancel each other out. Meters on top, meters on the bottom, that means they cancel each other out. Miles and meters, they both measure length, so I can put them in the same ratio. There's just two measurements of a length. So what do I do here for the numbers is I put down the conversion. How many meters are in a mile? How many miles are in a meter? Well, if you run track and field, you know that 1,600 meters is a mile. Is that not exactly 1,600? But we'll use that. 1,600 meters is 1 mile. All right? So if I were to end it right here, and I would just do 72.5 times 1 equals, divided by 1, and divide by 1,600, I would end up with the units of miles per second. I would figure out how many miles per second he traveled. I don't want that. I want miles per hour. So I need to convert one more time. I don't want seconds. The thing that I want on bottom is hours. I want something per hour. When it says miles per hour or meters per second, the thing that you say second is on bottom. So I want hours on the bottom. Let's write hour. And I want seconds to go away. So since it's in the bottom, I have to get rid of it so it goes on top. Seconds goes on top. And seconds will cancel out. So then I would be left with everything is canceled out except for miles per hour. Here I put my conversion here. 1 hour is 3,600 seconds. And you know that because it's 60 seconds in a minute and 60 minutes in an hour. That's just one conversion to know. There's 3,600 seconds in an hour. So if you start now and count to 3,600, 1, 100, 2, 100, 3, 100, it would take you an hour as long as you stay consistent. So now I know that my units are correct because everything cancels out except for miles. An hour, I know I did it right. Now I just have to do the right math. So 72.5 times 1 times 3,600. It equals, then divide by 1, divide by 1,600, divide by 1. Really, you don't have to divide by 1 because it gives you the same number, so I'm just going to divide by 1,600. And that is saying 163 miles per hour. All right, like that. You can also write this. It's the same thing. So instead of writing MPH, I'm going to write miles per hour, like that, because it's really what you're saying. So another thing in physics that's going to come up, especially near the middle of the year and in the later part of the year, is something called standard form. I'm going to show it to you now because it is pretty useful, especially when you deal with really, really big numbers or really, really small numbers. It's easier to use this form if you know what it does, right? So standard form, there's kind of two things to know about standard form. First thing you need to do is you need to convert it to the right units. We're going to focus on these 3 units: meters, seconds, and kilograms, the MSK system. So if you're given a length, you need to convert to meters. Not inches, not feet, you need to convert to meters. If you're given time, you need to convert to seconds. Not hours, not days, it's seconds. And if you're given a mass or a weight, make sure you convert to kilograms, at least to start, all right? So we'll talk about that soon. Then once you have your conversion, then you write your conversion in scientific notation. Now, scientific notation is a special way to write numbers that are really small or really big, right? And there's kind of steps to it. So step 1, you find your first non-zero digit. So like 1 through 9. Find that digit, write that down, whatever number that is. Then you put a decimal point after that digit, and write the next 2 digits after the decimal point. 05, 97, whatever it is, whatever the next 2 decimal points are. Now technically, there's rules to that, like depending on sig figs and stuff. I'm not going to worry too much about sig figs. Just write the next 2 for this class. Then you're going to multiply that number by some power of 10, like 10 to the 5th, or 10 to the 9th, or 10 to the minus 13th, to get back to your original number. So I think the best method to do this is to show you with examples. All right? Example number 1. Speaking of Mario, it's me, Mario. Turn this a little bit. Mario's height is 4 feet 8 inches. Convert that to standard form. All right. Oh my gosh, 4 feet 8 inches. That's a feet in inches. What should we convert that to? Well, meters, seconds, and kilograms. We're going to convert to meters. That's the length. So we're going to write down 4 feet 8 inches. Another way to write that is 4 feet is 48 inches. Add on 8 is 56 inches. So 4 feet 8 inches is another way of saying 56 inches because it's 4 feet is 4 times 12. I'll even write that out. 4 times 12 equals 48. I'm going to add on 8 to it because it's 4 feet 8 inches. 56 inches, right? We're going to convert that to meters. So we're going to multiply by the conversion factor. We don't want inches. We want to get rid of it so it goes at the bottom. We want meters to replace it. So inches cancels out with inches. We're left with meters. Now we just need to know the conversion between inches and meters. That's why I give you that conversion sheet. There are 39.37 inches in 1 meter. I know, I just get my calculator here. I'll multiply 56 times 1 equals, divided by 39.37, and I get 1.42 meters. Now, it says to write in standard form, so I should write that in scientific notation. So what I'm going to do is I'm going to multiply by 10 to some power to truly write in scientific notation. Now, if I multiply 1.42 times 10, I get 14.2. If I multiply by 10 to, that's the same thing as saying multiply by 10 to the first. If I multiply by 10 to the second, I get 142. If I multiply by 10 to the third, I get 1420. Right? I don't want that. If I multiply by 10 to the negative 1, I move the decimal place this way, I get 0.142. If I multiply by 10 to the minus 2, I get 0.0142. I don't want that either. So what you do is you multiply by 10 to the 0, because that's just multiplying by 1. You might write my units there. So the correct answer is 1.42 times 10 to the minus 10 to the 0 meters. This is one case where it's kind of pointless to use standard form, because you're essentially multiplying by 1, which is useless. But there are very useful examples. For example, the average distance from the Earth to the Sun is 93 million miles. 93 million miles. We're going to convert that to standard form, because if we try to use 93 million miles when we do our math calculations for physics, it's going to be a mess, because the units don't work out, the number is completely arbitrary. So we're going to convert that to standard form. So standard form, step 1. Let's convert 93 million miles. This is miles. Let's convert that to the right thing. Seconds, kilograms, or meters. It's measuring length, so it's meters. So, I write my conversion here. So miles goes on bottom. And we want meters instead. Meters goes on top. There's 1,600 meters in 1 mile. I multiply that out, and I get my answer. 93 million times 1,600. I get, oh my gosh. It gave me a weird number. So 1, 4, 8, 8, 7, 8, 9, 10, 11. It gave me this really big number. Miles. Oh my gosh. Sorry, meters. Meters. Symbol for meters is just M. Now, that's a really big number. It's hard to write that number. And it's hard to punch that number in the calculator because it's so big. But one way to do that is to write this number in scientific notation. So let's follow the rules. Rule 1, write the first non-zero digit. Well, the first non-zero digit, we start from the left, is 1. 1. Put a decimal point. Here's my decimal point. Boom. Then write the next 2 digits. 4, 8. And actually, I should go and see what the next digit is. It's an 8. So I round up to 49. So 1.49. Step 3. Multiply by some power of 10. So I multiply by 10 to some power. Now if I multiply this by 10, I just get 14.9. That's not big enough. If I multiply by 10 squared, I get 149. That's not big enough. If I multiply by 10 cubed, it's 1490. It's not big enough. So what you do is I start here, and I just count over how many places I moved it. This would be 10 to the first, 10 to the second, 10 to the third, 10 to the fourth, 10 to the fifth, 10 to the sixth, 10 to the seventh, 10 to the eighth, 10 to the ninth, 10 to the 11th, 10th, 10 to the 11th. So I have to multiply by 10 to the 11th power. And this is actually my answer right here. 1.49 times 10 to the 11th meters. All right, let's do one final example. Convert 0.1 nanometers to standard form. Now, that's about the size of an atom, the average size of an atom, 0.1 nanometers. So start with what you know, 0.1 nanometers, that's the length. We're going to convert to meters, 0.1 nanometers. We're going to convert to meters. So we want meters on top. Meters goes on top. Nanometers goes on bottom. Now in your conversion, it says 1 meter is a billion nanometers. So 1 with 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. So nanometers gets canceled out. We're left with meters. So 0.1 divided by a billion is 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1 meters. Now we're left with a really, really small number, 0.000, like a bunch of zeros and 1. It's hard to work with, so we're going to write that in standard form. Now, standard form, we convert it to meters. Step 2, we're going to write in scientific notation. So the first non-zero digit is 1. These are all zeros. The first non-zero digit is 1. So 1 point, write the next 2 digits. Now there's no digits there, so if there's not digits there, you can just assume there's zeros. 0, 0, 1.00. That's step 2, times 10 to the some number. Now we have to figure out what power of 10 do we need to make this so that it gets back to the original number. Well, if we start here, 1.0, and we're going to multiply by 10 to the negative 1 and move it to the left. Multiply by 10 to the negative 2, moves it left twice, 10 to the negative 3, 10 to the negative 4, 10 to the negative 5, 10 to the negative 6, 10 to the negative 7, 10 to the negative 8, 9, 10, and 11th. So we're going to multiply by 10 to the negative 11th, and that's going to be meters. A very small number. So when you're dealing with really, really big numbers or really small numbers, this comes in handy, especially if you're dealing like really, really big numbers, really small numbers. So hopefully that makes sense. Take some practice, ask some questions along the way, and best of luck.